Okay, it took a little longer than I thought it would, but that's fine. So we're talking about our Ka and Kb expressions. Yeah, there are notes in the back, right? Yeah. Sorry, we talked about Ka expressions. You don't know what the hell a Kb is, but you can probably guess. A Ka is an equilibrium constant for an... Okay, Kb is a equilibrium constant for a base, right? Okay, so it's a Ka is acid plus water makes hydronium. Good, acids make hydronium in water, right? A base, what do bases make? Bases make hydroxide. Okay, that'll be important a little bit later. Okay, let's scooch. We went through here and we just talked about what makes something a strong acid or a strong base, right? Strong acids ionize 100%, weak acids don't. And then we talked about, okay, a little bit ice table stuff. When you're calculating the Ka of an acid, you just do it your regular ice table, right? Take your changes into account and make your Ka. Like, this should all basically be old news. But this is where it started to get weird. This is where it was like, whoa, Walton, what are you doing? Why are you doing this? Get out of my face, okay? This is the part that really starts to screw people up. Predicting the pH and hydronium ion concentration of a weak acid is hard. Predicting the pH of a strong acid is super duper easy. Strong acids are super easy. 100% ionizes. So whatever the concentration of the acid is, that's the concentration of your hydronium. Then you just negative log to get your pH, whatever. Here, I started with 0.3 mole per liter of my weak acid. Is that how much hydronium I'm going to get at equilibrium? Does all of this turn into hydronium? No, and you have no idea how much will. You have got no clue how much of this stuff is going to turn into hydronium until you actually do the math. Okay? So here, a methanoic acid plus water is making hydronium and methanoate. And we're gonna lose just as much as we gain, right? Our hydronium gain is just as much as we lost. But here, the change from 0 to something is huge. Would you agree? If you have nothing of something and then you gain even a little tiny bit of it, that's a massive change. That's an infinite increase. Would you agree? Yeah. That's a huge change, okay? But when you have a buttload of something and you decrease by a tiny little bit, is that a huge change? No, that's not a huge change. It's like if you gave somebody who had never earned any money in their entire life, if you gave them $5, that's huge. That's a ginormous thing to them, right? $5, they can go buy things now when they never used to be able to buy things. But if you take a millionaire and you charge them $5 for coffee, they don't care. They have $1 million. $5 is nothing to them. You know what I mean? So here, you have to keep the X there. Here, do you have to keep the X there? No, you don't. You don't have to keep the X there. And remember, the only reason why we're allowed to do this is because this Ka value, is that Ka value super hyper accurate? No. There's like sometimes a 10% error in this measurement. So 10% error means that this number is really not that accurate. But that's fine, whatever, that's okay. We will always be able to use this approximation when we're using the approximation rule for acid-base equilibria because Kas they're all super tiny, they're all very inaccurate measurements. Let's do another example. When you get to university, you'll amend the approximation rule, but whatever, that's fine. What is the hydronium concentration of a 0.311 mole per liter solution of benzoic acid? How are we going to start this? What?
Write the equation.
Should we write an equation?
Yes.
Where does the hydronium come from?
Acid.
The weak acid. So let's write that. Let's write the relationship between the weak acid and the hydronium. Benzoic acid, C6H5COOH, is going to react with water. And it's, of course, it's an acid, so acids make hydronium. And whatever the conjugate base of benzoic acid is, whatever it is, C6H5COO minus. Now this is tough. In the previous chapter, we used to be able to say something, something, something initial, something, something, something equilibrium, and we knew we had to make an ice table, right? That was the idea. Now, all of that information is implied. You have to know that information is hidden in here. What is the hydronium concentration of this solution of a weak acid? How much hydronium do you start with in pure water?
0.
Basically 0, right? You actually start with 1 times 10 to the negative 7, but it doesn't matter. You basically start with 0. 0 of that and 0 of that. And we start with a concentration of 0.311 of this. If you don't add an acid to your water, can there be any hydronium in the water? Not really. If you don't add an acid to your water, can there be a conjugate base in your water? No, right? These things show up because this thing turns into those things. Okay, perfect. Do we care about water?
No.
Why?
It's heterogeneous.
It's a liquid and a heterogeneous. Man, how many times have I asked that question? Holy guacamole. So, does it give us any information about equilibrium, anything?
No.
No, not in the question. In your data booklet, does it give any information about equilibrium, anything?
Yes.
Yeah, it gives you the Ka value, right?
Yep.
What is the Ka value for benzoic acid? Jaden. 6.3 times 10 to the negative 5. Okay, if that's the only information we have about equilibrium, if that's the only thing, then we have to resort to using variables as placeholders, right? What's going to happen to my hydronium concentration? Is it going to go up or down from 0? Can it possibly go down from 0? No. Can you decrease if you start with nothing? No, it's not possible, right? So plus x, and minus x. Why are they all x's?
We don't know.
Because we don't know when all the coefficients are 1, right? So, okay. So this is going to gain an x, this is going to gain an x, and this is going to lose an x. So we're going to end up with 0.311 minus x. We're going to end up with x, and we're going to end up with x. Something. We know we're going to get something, but we don't know what it is yet. That's the whole point. Now, if I start at 0 and I gain x, is that a big deal? Should we keep this x here? Yeah, that's a super big deal, right? If I start at 0.311 and I lose x, and I know this change is tiny, teeny tiny. Sorry, what's the Ka of this acid again? 0.000063. That's a tiny K value. It's so tiny, right? 1 out of 20,000 of these is going to react, right? So yeah, you're going to get a small change, but it's big compared to 0. You're going to get a tiny change compared to 0.311. So that's the reason why we're allowed to do this. So let's do this. The Ka is equal to all of this junk, right? So So in this version, it's x times x divided by 0.311 minus x.
What if I keep the x and I didn't like
X squared?
Yeah.
Yeah, that's fine. That's
Yes.
better. That's better. I'm just trying to show people that it's products multiplied by each other and then reactants, right?
No, I mean the x, the 0.311 minus x. What if I keep this x out of it?
Oh man, if you keep it, woo!
And then like like how we did it from the first.
Well, you can't square root this. You cannot
okay.
square root this because what is x times x?
X.
It's x squared, right?
Mm-hmm.
So this is actually x squared over 0.311 minus x. Now, oh hi! I could try to square root this. I could try, but can you square root a non-square at the bottom?
Oh no.
No, you can't.
Yes.
Sorry, I'm sorry, everyone.
It's official business. Don't worry about it.
School, stay in school.
Yeah.
Let me stop it. You look enjoying sorry. I thought you gave it to give it to
Okay, so we could, if we wanted to, we could try and square root this. But what's going to happen is we're going to get a square root radical on the bottom, and that square root radical is going to be an absolute nightmare to deal with. Like it's going to be such a nightmare. So no, you cannot use the square root approximation or the square root approach to this. Now, what are some other ways that you could do this? Yeah.
Well, why don't, like, you know how, like, when we were doing it last time, we just, like, multiplied to get it on the other side and then square root it? Why can't we do that?
Okay, so let's multiply, and then let's square root. Like, are you saying leave the x in and do all this
Yeah,
stuff?
like, how come last
Yeah.
time we could leave the x in and then we can't?
We couldn't leave the x in last time. Here, we assumed it didn't exist.
I never did that.
Okay, well I did.
Like the ice tables before?
Oh, like last chapter?
Yeah.
Yeah, we can't, like, if we do that, let's just really quickly take 20 seconds and do this. Don't write anything down, just eyes up at the front, please, okay? Okay, this is an approach that will not work, okay, unless we do some things. So, let's go ahead and do that. Let's take this and let's multiply it up to the top, right? And so we're gonna get 0.311 minus x times Ka equals x squared, right? So then I have to distribute the Ka into the brackets. So I get 0.311 Ka minus x times Ka equals x squared. Now, I don't have an x squared here. So if you square root this, if you square root that side and then square root this side, keep in mind this is a binomial, but whatever. If you square root this, you will end up with a square root x and an x. This is going to become this is already a quadratic equation. You can't square root a quadratic equation unless it has perfect roots. Okay? So what I'm trying to say is you can't do the square root approach because when you square root the bottom value, you cannot square root a binomial and have it end up being really, really nice. That's just not something that's possible. Is that okay? Kind of, sort of, a little bit?
So how do we know, like...
Yeah.
Like, is it always the KC, we can keep the x, and then when it's Ka, you get rid of the x?
Yeah, why? Because all of the KAs in the data booklet are really small. They're all really small and inaccurate. But if I gave you a Ka of 54, that Ka is a hyper accurate number. We know that that number is approximately 54. Okay, it's not small enough for us to use this approximation. Hopefully that makes sense. Yeah. So anyways, there are other things that we can do. If you don't like, if you don't like ignoring this minus x, you don't have to. What are some other ways that we could find the solution to this? People who are in math 20-1 or 30-1 should know. We could just put this as y1 in our calculator. We could put this whole thing as y2 in our calculator, and we could just solve wherever they intersect. Right? That's something that you could do. You could rearrange this, just like we did before. We could rearrange this and get this, and this is now a quadratic equation. We can use the quadratic formula if you wanted to, right? Scott?
For the putting it into your graphing calculator and solving it,
Yeah.
Since the Ka values are so small, it's and the graphing calculator works based on pixels.
Yeah.
It gives you a ridiculous number that's so hard to actually get to even intersect it.
Stick around at lunch and let's try it. Like, let's just see, because that's the approach they teach at Hunting Hills. They don't teach the approximation rule. They teach graphing, because every single student in their classes has a graphing calculator, and they teach the graphing approach. So if you want to walk through it, we can walk through it together, and I got no problem with that. And we'll see if you're right and we'll see if you're wrong, because whatever, doesn't matter. Anyways, okay, back to writing stuff down. Boom. Okay, let's get back into it. So again, let's assume that this change doesn't exist. We will approximate this. What's 300 million minus 1? Still 300 million, right? So that's what we're doing. We're just assuming it's too small of a change to be able to influence anything. So all we have to do is rearrange this. How do I get x by itself? In here, if you had this, how would I get x by itself? Multiply by 0.311, right? So x squared is going to be Ka times 0.311. And then I'll just square root both sides, right? That's super easy. That's way easier than any other approach. So we're going to get x is equal to the square root of the Ka, 6.3 times 10 to the negative 5, times our original concentration. Hopefully you get 4.4 times 10 to the negative 3. Is that what you got? Once we've rounded properly, 4.4 times 10 to the negative 3 moles per liter. So this is, I would like you to listen back up again. What does x represent? In this problem, what does x represent? It's the hydronium concentration at equilibrium, right? That's the hydronium concentration at equilibrium. So if we wanted to, we could take the negative log of that value and we could get the pH of it now, and that would be totally fine. Let's take a look at this solution, and let's take a look at the previous solution, and let's see what they have in common, okay? So let's take a look at this. At the end of the day, what did we have to do? We had to take the square root of the Ka and the original acid concentration. In the previous question, what did we have to do to solve this? We had to take the square root of the Ka and the original acid solution. Do you see what I'm talking about? There is a super big shortcut here. If you wanted to, if you understood all of the chemistry, you could jump straight to, well, Ka is going to be x squared over the original acid concentration. And you can just solve for x. That's like the shortcut to being able to do this. But this isn't going to help you if you don't understand the context of the situation, right? If you use this at the wrong time, then you're hooped. Okay, so I want you to be aware. The the for sure way to do this, the way you can do this 100% every single time, set up an ice table, do the approximation, do all the hard work, right? It's longer, but it's better for you. If you understand this straight out of the gate, you can just jump straight to there. That's totally fine. Okay? So let's try and use that approximation rule to be able to help us here in a second. So we're set up with this conundrum. Which solution is going to be more acidic? A 0.5 mole per liter solution of phosphoric acid, which is a weak acid, or a 0.1 mole per liter solution of hydrobromic acid, which is a strong acid. What does your gut tell you to do? Which one of these is going to be more acidic? The strong acid or the weak acid, or the high concentration or the low concentration? High concentration? If I have lots of acid, shouldn't there be lots of hydronium? But a strong acid, what? What does a strong acid do? Ionizes completely, 100%. So there's a little bit of a battle here. Let's work through this together. But I want to prove to you that every single time you're asked this question, it's going to be one answer. Every single time. Okay? So, what do you want to talk about first? The weak acid or the strong acid? Strong acid. Let's talk about the strong acid first. The strong acid is hydrobromic acid, right? So HBr is going to react with water to make hydronium and bromide. If I start with a 0.100 mole per liter solution, if 100% of this turns into hydronium, what will be my hydronium concentration in the end? 0.100, right? 0.100 mole per liter. So, without doing any math, without using your calculator, this is really tough. Without using your calculator, what will be the pH of this solution? How many zeros in front of this one? How many zeros are in between the decimal place and the 1? There are no zeros. Okay? So just negative log this. Go negative log that. Just do it. Is this a pH of 1? Yeah, that's what I'm talking about. All right, so this is going to be a pH of 1. To more specifically 1.000. Whatever, that's fine. It doesn't matter. Okay, was that easy? Our weak acids easy. Sorry, our strong acids easy. Yeah, strong acids are easy. We love strong acids. Strong acids is like, so all of this turns into that, blah, and just do the negative log. Okay, now let's do a little bit tougher. Now let's do the weak acid. It is phosphoric acid, so that's H3PO4 is going to react with water, but this time it's in an equilibrium. It doesn't react 100%. We're going to get H2PO4 and hydronium. Good. When you look at that, it should bug you, right? No, I was literally waiting for somebody to call me out. Be like, Walton, no, don't do that. Bad Walton, then squirt me with a water bottle or something. Bad dog. Okay. So, let's just do this really, really simply, okay? We're gonna have 0.500 moles of this, right? We're going to have none of this. We're going to gain some. We're going to have some. We're going to lose some. And we're going to get 0.5 minus x. Remember, the shortcut for doing this is just Ka equals x squared over the original acid concentration. So, when we rearrange this formula, right? Times by 0.5 and then square root. X equals the square root of 0.5 times whatever the Ka of phosphoric acid is. What's the Ka of phosphoric acid? 6.1 times?
No, 6.9.
6.9 times?
10 to the negative 3.
10 to the negative 3?
Yes.
Boosh. There we go. Sky.
Phosphoric acid turns into
Dihydrogen phosphate.
which
Yep.
then turns into hydrogen phosphate
Yep.
acid.
Yep.
Do we have to do all of those calculations?
No.
Or just the one?
No, because every time you turn into a new acid, like because it's polyprotic, right? Every time we do that, what happens to the Ka every single time? What's the Ka of this is 6.9 times 10 to the negative 3. Look at the Ka of dihydrogen phosphate. What is it? Dihydrogen phosphate, the Ka is 6.2 times 10 to the negative 8. Okay, let's look at this, Sky. 6.2 times 10 to the negative 3 for this reaction. For the next reaction, 6.2 times 10 to the negative 8.
So it doesn't really matter.
It's like it's about 100,000 times weaker than this acid. So if let's say we gain 10 hydronium ions this time. Well, now the next time we'll gain 10 divided by 100,000. So there's the next change is so little that it doesn't really matter. Hopefully that makes sense. Okay, what did we get? I don't know.
I get 0.0587.
587, blah, 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 blah. It doesn't really matter, does it? Okay? So, this is the concentration of what? This is X, right? And X represents the concentration of hydronium. So how could I get a pH from this?
Negative log.
Go ahead, negative log this.
1.23.
1.23?
Like 1.0.
Yeah. So pH is 1.23. So which one of these is more acidic? Is the strong acid at a weaker concentration more acidic? Or is the weak acid at a stronger concentration more acidic? The strong acid. And I want to be very clear, even if this strong acid is 5 times less concentrated, even if we did 10 times less concentrated, right? 0.05, even then it would still be more acidic. The strong acid, as long as it's not 100 times more concentrated or less concentrated or whatever, the strong acid will always be more acidic, right? Because 1 out of 100 versus 100 out of 100. Does that kind of make sense? That strong acid will always be more acidic, and that'll save you time in the long run. Okay? Oh, I don't know. Hopefully that makes sense. Blah, 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 blah. Okay. All right. Let's move on. How do you solve a strong acid pH problem? Like, let's say I had 0.5 mole per liter of HCl. How could you get the pH out of that?
You have to react this with water, so I get the hydronium.
So this is the hydronium concentration, right? They're the exact same thing. Because does hydrochloric acid exist in water?
No.
No, it's just hydronium. It's hydronium and chloride. So that equals 0.5 mole per liter of H3O. They're the same thing. And then you just negative log that, right? Strong acids are easy, man. That's the concentration of my strong acid. It turns into hydronium, and then take the negative log. If you're solving for the Ka of a weak acid, what will you always have to use?
Ice table.
An ice table. You always need an ice table. If you're solving for the pH or the hydronium concentration of it should say of a weak acid, what should you use? We can use an ice table, or we can jump straight to this relationship. Do we know what HA means?
Yeah.
It's weak acid, any weak acid, right? Just whatever weak acid you want to talk about, right? Because a weak acid, how many protons does a weak acid give away when it reacts? 1. So you only need 1 to show that, okay? So that's what we can do. It's easy peasy lemon squeezy. Now, that's acids. And acids are great, and acids are fantastic. In fact, you love acids, because what do you talk about more? Do you talk more about acids or more about bases, typically? Yeah, acids. Acids is your wheelhouse, man. That's what I'm talking about. pHs, acid. Hydronium, acid. Acid, acid. Ka, acid. That's what I'm talking about. Everything is framed. Everything in your data booklet is framed around acids. But what else is there? Bases. We've got weak bases, man. Let's look at all the weak bases you could ever possibly try and talk about. Let's look at all those weak bases. Oh, I already had it up. Here we go. All of these weak bases, blah, 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 blah. All these weak bases, right? So we know how to solve for the pH of a weak acid. We don't really know how to solve for the pH of a weak base. When you're trying to solve for the pH of a weak acid, what do you have to use? Ka. What do you think you're going to have to use if you're solving for the pH of a weak base? Kb. And is Kb listed in your data booklet? No. Ka is listed, but Kb is not listed, okay? So here's what we're going to do. Oh yeah, diploma question. Okay. Here's what we're going to do. Kb is the ionization equilibrium constant for bases in water. We can convert from a Ka of a conjugate acid to the Kb of the conjugate base by a simple formula. This is the simple formula that's written right here. Kw is equal to the Ka times the Kb. If you want to find the Kb of a base, right? Kb for base, what other two things do you need? Kw and Ka. Do you know what Kw is? Did you memorize it? What? Why? Why didn't you memorize it? Because it's in your data booklet and you don't have to. Right? It's in your data booklet and you don't have to. Why would you memorize something if you don't have to memorize it? Do you remember what Kw is? It's on page 3 of your data booklet if you got to look it up. Do you see it? Kw, the auto ionization constant for water. Okay, so will you always have access to Kw?
Yes.
Yeah, boy. Okay. Now, Ka. You also need Ka in order to get Kb. Will you always have Ka?
Yes.
Do you not have a list of like 1,000 Kas in your data booklet? Yeah, you totally do. Where are they? Right here. Here's the list of all the Kas, right? So you've got this and you've got this. Can you always get Kb basically? Pretty much. Yeah, you can pretty much always get Kb. Okay, perfect. So let's do that. So I want to be very clear. From the data booklet, this is an excerpt from your data booklet. The ammonium ion, which one of these two things is the ammonium ion?
NH4.
NH4 plus, right? They're always listing the acid name here, so that's the acid. What's the conjugate base of the ammonium ion? NH3, otherwise known as ammonia, right? Okay, so ammonia. Now, this Ka deals with this thing, right? That thing turning into that thing. But let's try and calculate the Kb of NH3. The Kb of NH3. How can I rearrange this to get Kb all by itself? Jaden. Divide both sides by Ka, right? So we're going to get Kw divided by Ka. And I want to be very clear. It's the Ka of the conjugate acid, right? Of ammonium ion. What the hell is Kw? 1 times 10 to the negative 14. And the Ka for ammonium is 5.6 times 10 to the negative 10. You should get 1.8 times 10 to the negative 4? 5? 1.8 times 10 to the negative 5? Is that what it is? I'm looking for reassurance. Remember, I'm a little child and I need to be reassured at all points in time. Yes? 1.8 times 10 to the negative 5. Did we all get that? Does anybody not get that? It's okay if you didn't. We just have to learn how to use our calculators before the exam next Wednesday. You know what I mean?
1.7.
Whatever. Okay. All right. Whatever. 1.8 times 10 to the negative 5. Perfect. Boom. You just calculated Kb for conjugate base. That's what I'm talking about. Which is a stronger base? The carbonate ion or the cyanide ion? Now you can look at your data booklet and you can just immediately tell, okay? Use your data booklet and tell me which one is stronger, the carbonate ion or the cyanide ion. What does carbonate look like? CO3 minus, right? So here's CO3 minus, and what does cyanide look like? Cn minus. Which one of these is stronger? Which one's the stronger base? Carbonate, right? Big time carbonate. Why? Why is carbonate a stronger base? How do you know carbonate is a stronger base? Because it's lower on the list. It's closer to hydroxide, right? The closer you are to hydroxide, the stronger you are, okay? Now let's prove it. Let's prove it and justify it using KBs. Okay, so the KB of carbonate, how could we calculate the KB of a weak base? KW over the KA of its conjugate acid. What is the conjugate acid of carbonate? hydrogen carbonate, right? HCO3 minus. So we're using the formula that we literally just learned about 20 seconds ago, right? But we're going to use it a few times to make sure it's ingrained in our minds. 1 times 10 to the negative 14 divided by the Ka of that thing. 4.7 times 10 to the negative 11. 2.1 or 2.2 times 10 to the negative 4.
How are you doing that?
What do you mean, how am I doing that? I'm dividing two numbers. I'm taking one number and dividing another number. Sorry, I'm being facetious. I know that this is difficult, right? No, I get this. I get it. Okay, what's 10 to the power of negative 14 divided by 10 to the power of negative 11? 14 minus negative 11.
Oh, you just
Should be
made laws.
10 to the, yes, 10 to the power of negative 3, right? But then we're going 1 divided by a big number, so it's actually 10 to the power of negative 4. So, and then 1 divided by that is 2.127. So 2.127 times 10 to the negative 4. Perfect. Just doing some math, man. It's all good. Okay, that's the KB of this thing, right? Now, what's the KB of the other thing? Of cyanide. That's the worst sign. Hopefully you can see that's a CN minus. Whatever. What's the conjugate acid of CN minus?
Is it TN?
HCN. One times 10 to the negative 14 divided by 6.2 times 10 to the negative 10. 6.2 times 10 to the negative 10. I'm going to guess it's 1.6 times 10 to the negative 5. 1 point what? What do you get? Give me 3 extra digits, or three decimal places. 1.612 times 10 to the negative 5. Okay, which one of these is a stronger base? Don't look at the chart, look at the KB. Which one is a stronger base? Is carbonate a stronger base? Or is cyanide a stronger base? Carbonate is a stronger base. Why? If you had to write out an English full sentence, what would you say? Silence. You would say, carbonate is the stronger base. Because it has a larger KB. Wow. Is that okay? Not too bad? Alright. Okay. Now, KBs are exactly like KAs. Okay? What do bases make in solution? What do bases make in water? Hydroxide. So we can use all the same old tricks. All the same old tricks still apply, right? What's the approximation when we're doing when we're solving for like weak acids? Ka equals x squared over the acid, the original acid concentration, right? Now let's use that same shortcut. Now, if it was bases, what would it be for bases?
KB.
KB is x squared over the base, the conjugate base, right? The original base concentration. Does that make sense? That's only for weak bases, right? And what would we be solving for? What What did X represent in the acid version?
Hydronium.
Hydronium. Ooh. Okay. What is X going to represent for bases? Oh, that's what I'm talking about. See? Word association. Come on. All right. Come on. There we go. Practice. You could do that practice. Okay. Because KB values deal with bases, we need all the relevant information to be related to bases as well. If you see a base, turn it into, if you see a pH, turn it into POH. If you see hydronium, turn it into, nobody's using the voice, hydroxide. Does that make sense? This is like the dark side in Star Wars. You know what I mean? We never want to talk about it, but it exists, and it's just as important as the light. You know? No? Okay, whatever. We talk about acids all the time, but bases still exist, and there's a certain perspective of bases, right? POH is a base perspective. Hydroxide concentration is a base perspective. KB is a base perspective. If you see a base, you need all your stuff to be in bases, okay? Another way to calculate KB is by using an ice table, and this is the last thing we're going to do today. But this should be easy for you. Calculate the KB of an unknown weak base. What do you want to symbolize our unknown weak base to be?
HA.
We can't use HA.
A.
So what? AOH? We're not so something, something OH is like a strong base, right? But we need it to be a weak base.
HB.
So yeah, you could do B, you could do B minus, you could do A minus as the conjugate base of the acid, right? You could do X, you could do whatever you wanted, okay? You could just pick anything other than something OH and then other than H something. Because H something is acids, right? Would you agree? H something is for an acid. So you can just do something, that's fine. Calculate the KB of an unknown weak base if the concentration of the base is blah and it has a pH of blah, okay? So, all right, let's do that. Are we talking about bases here?
Yes.
Then let's turn everything in here into bases. What do you see that's in here that's written from an acid's perspective?
pH.
Oh, no. pH. Psst, no, get out of here, okay? pH, we got to turn that into POH. So let's turn that into POH. .44, I think, right? Good. Oh, that's what I'm talking about. POH is 5.44. Now, what does POH really mean? The POH is a measure of the hydroxide concentration. This literally means power on the hydroxide concentration. So let's calculate hydroxide concentration. 10 to the negative POH. 10 to the negative 5.44. This is the only thing I'm incapable of doing. To the power of something, to the power of a decimal point is, it's not physically possible for me to do.
3.63.
Just do it.
3.63.
63.
Okay, give me 6307 times 10. What?
Negative 6.
Is that okay? Good. Mole per liter. Perfect. That's our hydroxide concentration. Now, if it's asking for the KB, right? We want KB, that means we need equilibrium concentrations of everything. Would you agree? We need all the equilibrium concentrations. Do we have all the equilibrium concentrations? No, we're given the initial concentration of the weak base. What do you have to use?
Ice.
You've got to use an ice table. The reason why we have to use an ice table, initial concentration of that, equilibrium concentration of hydroxide. That's why we got to use an ice table. Remember, this is the last thing we're doing. Just calm down. It'll be okay. So our base, this is what I would do. I'd say our base is weak base. Boom, that's our base. Base plus water. What do bases make in water? Hydroxide. OH minus plus HB plus. Or whatever, it doesn't matter. It's whatever. So this is our conjugate acid of the weak base, right? So if we started with 0.34 of this, nobody cares about water. How much hydroxide did we start with in our initial pure water solution? How much hydroxide did we start with in pure water, right? 0 and 0. How much hydroxide did we get after we added the base?
Hydroxide.
Yeah, how much hydroxide did we get after we added the base? Once we reached equilibrium?
3.6.
3.6 times 10 to the negative 6, right? So we gained 3.6 times 10 to the negative 6. I'm just doing this because we're kind of running out of time. We gained 3.6 times 10 to the negative 6. Would you agree for every hydroxide we gain, we have to gain a weak acid, right? These numbers will be the same. So we're left with 3.6 times 10 to the negative 6 and 3.6 times 10 to the negative 6. Okay, if we gain this much hydroxide, how much are we going to lose of our base? Same thing, minus 3.6 times 10 to the negative 6. Now this is going to be weird. If you put this in your calculator, you're going to get 0.33999. It's like, this is an incredibly tiny change, but we still have to take it into account. You still have to take it into account, okay? There's no, why can't we use the approximation here? Are we using an inaccurate number anywhere right now? No, we're not. Okay, so we have to take everything into account. All right. The KB of this should be really easy, right? This times this divided by that. 3.6 times 10 to the negative 6 squared divided by 0.33999. And I'm foregoing a bunch of decimal places because we're running out of time. We have approximately 30 seconds left in class. We have approximately 0 seconds left in class. I don't know, do it at home or finish it right now. Hopefully, do you get 3.9 times 10 to the negative 11?
Yes.
Yes, we do. Okay. You have enough time. Tomorrow, we're going to do a couple more examples, but I'm going to give you like half an hour to 40 minutes to do an assignment. I would love it. Love it if you finish the assignment tomorrow. If you want the assignment today to work on it, because you can basically do everything on here. I'm just going to put it right beside there as you walk up to it. What? That's different than the major assignment, yeah.